Every year, thousands of students master every step of a mathematical procedure, yet find themselves paralyzed when the variables shift by a single degree. This failure rate persists even among those who have spent months memorizing formulas for CSIR-NET and TIFR. This occurs because most preparation treats mathematics as a mechanical checklist. You memorize an algorithm, plug in the variables, and execute the steps to reach a predefined numerical answer. Graduate-level problems require the construction of rigorous proofs to demonstrate whether a specific structure exists or if a certain property holds. Mechanical repetition offers no path forward when a problem demands you justify the validity of the operation itself. Overcoming this requires structural intuition, seeing the precise rules and logical constraints binding mathematical objects together. We build this by performing semantic deconstructions of canonical texts, parsing the exact wording to extract the underlying proof strategy. This series analyzes the core of the graduate canon: Munkres text on topology, Hoffman Kunze's linear algebra, and Rudin's real analysis. Engaging with these texts requires dissecting every condition in an axiom. You have to uncover why the author chose a specific constraint and how that choice dictates the logic of the entire chapter. For MSc students and PhD aspirants, this channel provides full semantic breakdowns of these chapters. We are looking for the internal logic that standard lectures often skip. To understand how these theories function in a competitive exam environment, we must first look at how the architecture is assembled. We begin with James Munkres' Topology, the primary text for abstract spatial reasoning. Most introductory explanations focus on physical metaphors, like turning a coffee mug into a donut. In rigorous mathematics, these visual shortcuts actually obscure the logic. Munkres defines a topological space without distance. A space is built by declaring which collections of points are open sets, satisfying three specific axioms. Here, continuity is redefined. A function is continuous if the preimage of every target open set is also open in the domain. Munkres relies on these set-theoretic rules, forcing you to abandon geometric intuition for algebraic consistency. This level of abstraction is necessary for CSIR-NET questions that present non-standard topologies, spaces where your physical gut feeling about distance is intentionally used against you. Working through Munkres systematically removes your reliance on Euclidean assumptions. You learn to operate in spaces where proximity is defined by set membership rather than a ruler. Mastery in topology comes when you can navigate and map these abstract spaces using only the internal logic of the axioms. We move from spatial logic to operational structures with Hoffman and Kunze's linear algebra. Undergraduate courses often emphasize the computation of matrices. Hoffman-Kunze shifts the focus away from these grids of numbers toward the study of abstract spaces. The text centers on the vector space over a field. These objects are governed by addition and scalar multiplication, completely independent of any Cartesian plane. A linear transformation acts as a structure-preserving map. It partitions the domain, sending a specific subset, the null space, to 0, while mapping the remainder into the range. Hoffman-Kunze uses these partitions to derive the rank nullity theorem, determining the transformation's behavior without row reduction. This relationship between null space and range provides the criteria for operator invertibility. TIFR exams frequently test this. They present an abstract operator and require you to deduce its properties based on how it partitions the space, rather than how its matrix is calculated. Hoffman-Kunze treats linear algebra as the study of how transformations preserve the fundamental properties of the underlying space. The final pillar is Walter Rudin's Principles of Mathematical Analysis. Baby Rudin is known for its semantic density and its refusal to provide explanatory padding. Every sentence is a load-bearing element of the logical structure. Real analysis provides the logical framework to determine if and why a limit exists, moving from the computation of basic calculus to formal verification. Rudin uses the epsilon-delta definition of a limit to remove ambiguity from continuity. Defining an epsilon boundary forces a delta boundary containing the function's behavior. This rigor allows Rudin to construct metric spaces, generalizing proximity into 4 distance axioms. His incredibly efficient prose compresses pages of standard explanation into a direct, logical sequence. This uncompromising approach is vital for the true-false sections of the IIT JAM, where any lack of analytical precision leads to immediate error. The difficulty of the text serves a specific purpose. It forces the reader to abandon their visual assumptions and rely entirely on formal proof. In real analysis, you must justify even the most visually obvious properties using airtight, unassailable logic. While we study these texts individually, modern mathematics operates at the overlap. Topology, algebra, and analysis are interconnected. The most challenging exam questions operate at these intersections. Success requires shifting between these different frameworks within a single problem. You might be asked to prove the topological properties of a specific linear operator within an analytical space. Rote memorization fails here. You cannot use a memorized formula when the problem requires you to bridge 3 different mathematical disciplines. Our goal is to unpack these chapters line by line, building the structural intuition needed to navigate these cross-disciplinary problems. This series is built specifically for MSc students, CSIR-NET aspirants, and those who value the rigor of pure mathematics. Every video in this series is free. These breakdowns are designed to provide a direct path to these core concepts for anyone with the patience to work through them. Subscribe now to ensure you don't miss a single chapter breakdown in this series. Share this with anyone currently preparing for TIFR, IIT JAM, or PhD entrance exams. We begin with the first chapter of Munkres. Comment below and let me know which theorem or